Swayam Prabha. Digital India. Educated India.
In my previous session, I had discussed the second process in the digital image processing flow chart, and that was pre-processing. In this, we had undertaken the task of making the image planimetric to the actual ground through the process of spatial interpolation and intensity interpolation. In this particular session, I am now going to focus my attention on the third process involved in digital image processing, and that is image enhancement. Image enhancement is a process of making the visual interpretation and understanding of imagery easier. The advantage of digital image is that it allows for manipulating the digital values of a pixel in an image. Although radiometric corrections for illumination, atmospheric influences and sensor characteristics may have been done prior to distribution of data to the user, the image may still not be optimized for visual interpretation. One of the aims of digital enhancement is to amplify the slight differences for a better clarity of the scene. This increases the separability, that is contrast, between the interested classes or features. The digital image enhancement may be defined as some mathematical operations which, when applied to digital data, improves the visual appearance of an image for better interpretability and subsequent analysis. Since the image quality is a subjective measure and may vary from person to person, thus there is no simple rule as such that a particular technique may produce a single best result. Normally, two or more operations on the input image may be sufficient to fulfill the requirements of the analyst, although the enhanced product may only contain a fraction of the total information stored in the original image. So, with this background, now let us look at what are the various methods of contrast enhancement. The contrast enhancement methods can be categorized as follows: linear and non-linear. In linear enhancement techniques, the mathematical implementation is on the basis of a uniform slope, while in non-linear methods the enhancement is done on the basis of using a varying slope. So, now let us look at some of the linear methods which are commonly used. The different methods for linear enhancement are as follows: minimum max stretch, or in short min max stretch, percentile stretch, and the third is piecewise linear stretch. So, let us look at the different methods of linear stretching one by one. The first one is min max stretch. Well, this is one of the simplest methods for improving the contrast. Here, the lower and upper values of the histogram of the original image are made to fit between the full ranges of the brightness scale. The lower value of the original histogram is assigned a 0 brightness value, while the upper value of the original histogram is assigned a value of 255 if a 8-bit brightness scale has been adopted. Well, this will vary as per the bit scale adopted for each of the image. In between all the intermediate values of the histogram are reassigned new brightness values by linear interpolation and are expressed as by the relationship x nu is equal to x I n minus x min divided by the difference of x max minus x min multiplied by x r, where the terms x nu is the new brightness value of a pixel after stretching, x min is the minimum brightness value of the original data, x max is the maximum brightness value of the original data, x in is the original input brightness value, x r is the range of the brightness scale adopted, that is between 0 to 255 for a 8-bit data. Here in this particular slide, a graphical representation of min max stretch has been provided. We can see that the original histogram has been drawn with the brightness values plotted against the frequency, and we find that the x min, that is the minimum value of the histogram, is not coincident or equal to 0 of the brightness scale. It is slightly shifted towards the right hand side. Well, there can be many reasons for this, but it is a clear indication that we are not using the full brightness scale. Similarly, the x max value does not coincide with the maximum value of the brightness scale. It is slightly shifted leftwards. Again, it means that the brightest object in the image is not corresponding to the brightest color in the brightness scale. In between, that is, we are having the different input values of each pixels, and this is represented as x in. When we perform the minimum maximum stretch, this is a activity wherein the lookup table of the computing of the display device would be modified. So, we have to now identify a mapping function. In this particular case, the mapping function would be a linear one between the values of x min and x max projected between the range of the brightness scale adopted, that is between 0 to 255. Once this mapping has been done, it provides to the device displaying the image how the x minimum value is to be projected and how the x max value is to be projected onto the display device, with all the intermediate values being distributed linearly in between this particular range. Having done this, the image undergoes a change in the visual appearance on the display device, and once the analyst again performs the determination of the histogram of the modified image, the resulted histogram can be seen at C, wherein now we find that the histogram shape has undergone a significant modification. It is much more flatter than what we have seen for the original one, and that the values of the histogram are starting from 0 to 255, thereby utilizing the whole range of the brightness scale. This can be seen in this particular slide, wherein on the left hand side we have the original data. The visual quality of the data is such that we can only see a sharp curved arc in the whole image, and the rest of it appears to be black, which means that the information that has been collected is collected within a very narrow range of the histogram, and thereby we are not able to decipher any of the information as portrayed in the original histogram. By performing a simple linear stretch using min max, one can improve the visual quality, and we can see on the right hand side that how the image quality improves significantly. Let us have a look at another image which has been subjected to min max stretching. In this particular image, one can see that this is an area where there is lot of farmlands, and in between there is a road which is going. The original image tells us that the representation of the various informations within this particular landscape appears to be merged, and there is no distinctiveness between different types of objects. On examining the original histogram, we find that the minimum value of this particular data set is 15 and maximum is 184 within a brightness scale of ranging between 0 to 255. By performing a minimum min max stretch, now this particular image on the right hand side has undergone a substantial change in its visual appearance, and one now can see the manner in which the various information features which are lying, areas which were earlier appearing to be as gray have now got converted into dark patches, suggesting that these could be either moist soil patches or maybe water bodies of shallow depth. In between, the road has become much more clearer and sharper in comparison to the agricultural areas. Sometimes when min max stretching is performed, the tail ends of the histogram are long, resulting in no improvement in image quality. Under such circumstances, it is better to clip a certain percentage, that is 1%, 2%, 5% of the original data from the two tail ends of the histogram of the original image. This method is known as percentile stretching. In this particular slide, we see a original histogram which has been represented to have a long tail. The minimum value and the maximum value in this particular histogram of the image are very close to the ranges of the brightness scale. However, when we perform the min max stretch, it may not bring about a significant change in the image visual quality. So, how do we improve this type of a histogram? Best is identify a range which could be 1% or 5%. In this case, we have adopted a 5% cutout value. So, what happens is, physically all the data in this particular range of 5% from the top and from the bottom of the histogram are cut out, and wherever these cutoff values are obtained, between these a linear transformation function as adopted for min max stretch is carried out. The net impact of the adjusted histogram can now be seen at figure C, wherein we see that the histogram has now is having a very distinct change in its shape. By and large, it has risen from the base or from the x axis by a significant value corresponding to the frequency at the cutoff, and also the shape of the histogram has become more rounded, thereby giving a very good representation of the image. In this particular slide, the same image of the bay area wherein the sandy portions were being observed have been again taken up, and now we can see is that a region which we had called it as an estuary, now we can find that this is probably a sort of a bay area having lot of other informations or surrounding areas such as residential area in its close vicinity. Also, the appearance of the barren mountain tops have also become much more clearer than in the previous case wherein min max stretch had been applied. Similarly, when we look at the farmland image, we find that by applying a 5% stretch, the appearance of the road has become much more clearer than in the original image. Also, the variation of the soil moisture in the adjoining fields have also become much more distinct. The bare soil field patches are being depicted in very bright white color, whereas varying moisture intensity bearing fields are now ranging in gray to black. Next is piecewise linear stretch. When the above two techniques of linear enhancement are suitable, when the histogram of the input image is unimodal in nature, that is, it has only one peak. However, this may not be the case and the histogram is multimodal in nature, indicating that there is more than one object in the image. Under such circumstances, the histogram has to be stretched in pieces. It could be possible that the slope of the transforming linear function defined having varying gradients. In this particular slide, we can see that the original histogram has two multimodal shape. There are two peaks which are being defined, and in order to provide a good stretching or contrast enhancement, what we may do is break it up into three different regions having three different linear functions of varying slope. By adopting such a procedure, the image histogram gets improved again in terms of the shape and also in terms of the nature that is portrayed. Having had a look at the linear methods, now let us look at the non-linear methods which are there. First one is histogram equalization. The image histogram is used for the more sophisticated methods of contrast enhancement. The first of the two methods to be described here is called the histogram equalization. Its underlying principle is straightforward. Each histogram class varying between 0 to 255 in the displayed image must contain an approximately equal number of pixel values or frequency as, and that the histogram of these displayed values will then be almost uniform. If this is done, the entropy of the image, a measure of the information content of the image, will be increased. Due to the nature of the digital images, where pixels can take only discrete values ranging between 0, 1, 2 or 255, it is possible that there may be too many pixel values in one class even after equalization. However, it is not possible to take some of the values of that class and redistribute them to another class, for there is no way of distinguishing between one pixel of x and another of the same value. So, in order to perform this distribution, we undertake a process of determining a target pixel, which we call it as NT, and this can be easily found by dividing n, that is the total number of pixels in the image, by 256, that is the number of histogram classes, which is the number of intensity or brightness levels in the image. Next, the histogram of the input image is converted into a cumulative form with the number of pixels in each classes 0 to j represented by Cj. This is achieved by summing the number of pixels falling in class 0 to n of the histogram, that is, the histogram classes are labeled 0 to 255 so as to correspond to the pixel values on a 8-bit scale. So, Cj can be expressed as equal to n0 plus n1 plus n2 to nj, where nj is the number of pixels taking the grayscale value of j. If we find that the class number j0, which is the first to exceed the target value nt, then we set the LUT so that all input values of j0 or less map to an output value of 0. Now, we find the class number j1, which is the first to exceed twice nt, and set the LUT so that all input values greater than 0, but not greater than j I map to an output value of 1, and so on until all output values in the LUT have been filled. Sometimes 2 or more j values may map to the same output value. In such cases, the greatest j I value is chosen. This implies that there may be a fewer levels in the output image than in the input image. To explain this particular procedure, let us look at a small example of histogram equalization using the histogram of an original data having a 4-bit, that is 16 levels of brightness, for a image size of 512 by 512. That means, we are having 16 levels of brightness and the total number of pixel in the image are 114. All right. So, if I divide this value by 16, it gives me a target value of 16,384. So, this would be the value which we will now consider to remap the classes or the intensity levels in the histogram, so that the image gets improved. Let us look at the table which is given here. So, for each of the brightness level, the number of points have been indicated. So, for brightness level 0, we have 1311 points. So, brightness level 1, we have about 2622 and so on. With the help of these frequency values, what we do is we prepare the cumulative frequency, which is shown in the third column, and one can see that at the bottom the total number of points in the image should be equal to the cumulative frequency value at the last brightness level, which is equal to 2,62,144. Now, our task is to remap the old LUT value such that we can improve the image representation. So, taking the target value of 16,384, we start to now look at the cumulative frequency values at each brightness level. So, at each brightness level 0, the cumulative frequency is 1311, which is far more less than the identified target pixel value, that is NT. So, we continue to the next brightness level. The figure is 3933. That means, when we combine brightness level 1 and 2, only 3933 points are present in the image, which is an indication that we still have scope to merge large number of brightness level. And what we find is that at brightness level 3, the total cumulative frequency is 18,352, and this is greater than 16,384. So, the brightness level 3 of the original histogram will now be assigned a value of 1, and all the previous brightness levels, that is 2, 1 and 0, will now be redefined with a new brightness scale value of 0. Then we proceed ahead, and now we raise our bar of examining to twice the NT value, which will now be something like 32,768. With this value, now we start to compare beyond the brightness level 3, because that is the pair where we have found that it has exceeded 1 NT. So, brightness level 4, the cumulative frequency is 31,460, which is less than twice NT value. So, this level now would be assigned a value of a new brightness value of 1. But when we look at the brightness level of 5 in the original level, the cumulative frequencies at this point is equal to 56,364, which is more than thrice the target pixel value. So, this particular brightness level of 5 in the original image will now be assigned a value of 3, and in this manner we continue and proceed ahead to examine each of the cumulative frequency values which are there and remap the old brightness values to the new brightness values. As I have said earlier, one can very well see that there are gaps in the assignment of new brightness values. For example, brightness value 2 is not there. Similarly, brightness value 4 is not there. We are also missing the brightness value 6 and 7. So, it is all dependent by the manner in which the number of points which are present up to a particular brightness level, which helps us in reassigning. So, we are trying to redistribute the information across the image. Interestingly, if you see, beyond brightness level 10 in the original image, all have been assigned the maximum value of 15 in the 4-bit brightness scale that we have adopted. So, having done this task, now we can identify how many pixels have been now readjusted into the new brightness scale that we had adopted, and we find that there are 9176 points having brightness level 0, whereas in the original data it was only 1311. Similarly, when we examine the brightness value 1 in the new adjusted LUT, we find that now it consists of more than 22,284 points, whereas the original histogram contained only 2,622, which means there has been a significant amount of information change brought about by adopting histogram equalization procedure. What we find in this particular process is that the information is made to be more compressed around the tail ends and expanded in the central portion of the histogram. That is, there is more stretching of information in the central portion of the brightness scale, thereby enhancing the features and compressing the features at the tail end. This particular slide shows the beach area of the, and what we find here is that in this particular image there is a slight over brightening of the sandy portions in comparison to minimum stretch and percentile stretching which is there. That is, the information has started to blur a little more. Similarly, when we look at the image of the land of the farmland area, in this particular case we find that the information has now been represented much more better. There has not been over blurring of the white portions, but it is much more crisp. So, what we can say here is that there can be no general rule that a particular method will tend to portray. It will all depend upon the scene characteristics. For example, in the Bay Area, the sandy beaches, they got over blurred, more over brightening took place. Here in this particular case, no such phenomena has happened. However, the varying degree of moisture between present in the farmlands has been more exemplified and provides a better information to the analyst. We now look at the next non-linear method, which is the Gaussian stretch. Gaussian stretch method is based on fitting the observed histogram to a normal or a Gaussian histogram. A Gaussian or normal distribution can be defined by the relationship y is equal to 1 divided by under root of 2 pi sigma raised to the power minus x square divided by 2 sigma square, where sigma is nothing but the standard deviation of the information, and this has already been computed when the initial statistics was undertaken. So, now we are going to use a Gaussian distribution model to fit this information. The basis of this particular approach is that we are now going to take into consideration what is the probability of information as per a Gaussian distribution model and how does the original data set match to the Gaussian. The idea is that we have already defined in the early stages while discussing initial statistics that the data model that we adopt to collect information through remote sensing sensor is a Gaussian model. Hence, it is good that we adopt a similar distribution pattern in terms of the information content. So, in order to highlight the procedure that we adopt in Gaussian stretch, let us take the same example wherein we are taking a 4-bit data having 512 points by 512 points. What we do here is that first of all, on the basis of the standard deviation, we identify what is the probability factor based on which we find out what would be the Gaussian frequency. First of all, based on the number of classes of brightness that we have, we divide the sigma into small ranges between plus minus 3 and assign these values to each of the brightness level. So, for brightness level 1, a sigma value of minus 3 is adopted and this value is put into the equation where y will yield what would be the probability factor. This probability factor now works out to be 0.0020 and this factor will now be utilized to find out what would be the Gaussian frequency that the histogram should have. So, what we do is multiply this factor by the total number of points which is there and taking the integer value or rounding it off to the lower closest value, what we find is that the Gaussian distribution having 0 brightness level should be 530. Similarly, for brightness level 1, the standard deviation factor is now minus 2.6, corresponding to which we get the probability factor as 0.0033 and we multiplied this by the total number of points, which yields that a Gaussian histogram having frequency brightness level 1 will have 868 points. So, we continue this particular operation till we compute all the values for each of the levels of the histogram. Having done this, we now undertake the task of finding out which the cumulative frequency of the Gaussian distribution, and this is shown in column number 5. Now, we have already computed the cumulative frequencies of this particular histogram while we were discussing histogram equalization, and they have been shown in column number 7. Now, in order to now do the remapping, in this particular case, what we try to see is which frequency value in the original data where it exceeds the Gaussian distribution. So, what we find is that the brightness level 1 in the original histogram is to be compared with the Gaussian histogram. So, when we look at the brightness level 0, it has a cumulative frequency of 1311, and when we compare this to the Gaussian cumulative histogram shown in column 5, what we find is that this is exceeded at brightness level 1. So, the previous value is assigned to this particular original brightness level, that is brightness level 0 is assigned a brightness level of 0. Then we look at the next cumulative frequency at brightness level 1, and this particular value is exceeded at the brightness level at brightness level 2. So, it is now assigned a value of 1 in the new histogram. So, in this manner, the points or the new brightness values are assigned to each of the classes, wherein in this particular case we are matching the frequencies of the Gaussian histogram to the original histogram, whereas in the histogram equalization method we had identified a target pixel, and based on that, taking the integer value of the target pixels, the mapping was being carried out. So, one can say that in the earlier case it was uniform distribution of energy which was taking place. Here it is uniform distribution in terms of membership. So, based on this, we have now identified what would be the new values which would be there. The next table shows the new number of points which would be assigned at each level, and what we find is that in the central part, in the tail ends of the information, there is stretching of data, whereas in the central part there is compression of information which is there. So, if we look at the landscape data, that is the farmland data, we here wherein we are now looking at the analyzed data or the image using Gaussian stretch, we find that there is a loss of information in comparison to histogram equalization. The information in the darker side have now become more expandable, more understandable in comparison to the central area wherein larger grayness values are there. So, now let us look at the example that we had taken in the initial statistics, wherein an image, a TM data has been taken for consideration, and the original data shows that the minimum value in this particular case is 44 and the maximum value is 147, and there is a overall brightening in the image quality. We need to remove this particular aspect. So, this can be undertaken by looking at the histogram of the original data, and what we find is that the range of the values in the image is very small, and thereby we are losing lot of information. So, we first apply the min max stretch, and immediately there is a marked difference in the image. We can see all the sandy areas and the barren areas of the image are now much more clearer and brighter, and the forest areas which were earlier appearing to be slightly gray in color are now more darker, specifically the dense forest regions in the particular image. Also, some of the areas where afforestation activities have been undertaken, the representation of those patches are much more clear in the lower right portion of the image. If we look at the histogram of this particular image after stretching, what we find is that there is a significant amount of improvement in the distribution of the points in the histogram. The histogram has now expanded in range in comparison to the original data, wherein it appeared to be as if it was a sort of a column. Here it tries to look like as if it is a bell shaped information with a larger base. Then we look at the same image wherein histogram equalization has been carried out. As I have said, there is a tendency of over brightening, and this can be seen specifically in the middle left top part of the image, wherein barren lands have become much more brighter. In fact, the image representation has become very bad, that is because of the over brightening which has undertaken. However, varying forest classifications have become much more improved in this particular case. When we look at the histogram of the histogram equalization method, what we find is that there is a compression of informations at the tail ends, and the central part of the data has been stretched and expanded over the major portion of the brightness scale. When we apply the Gaussian stretch to this particular data set, what we find is that the barren areas on the top left hand corner, they are becoming much more distinct in their representation in comparison to dry soil, which otherwise in the previous case we found that they were getting merged together, their contrast was lost. So, this is probably because of the stretching which has taken place at the tail ends of the histogram, and thereby the representation of information of dry sand and dry soil has become much more distinct. The histogram here, what we find here is, in comparison to the original data set, it is still like a column like representation. However, the base of the data set has expanded and thereby bringing about a better improvement in the representation of brighter brightness scales. As I have said, these methods are all subjective and also dependent upon the location. So, depending upon the location, one may find that a particular method may be optimal in producing a good quality image. However, the same may fail in a different landscape, as we have seen, wherein we had taken a landscape which was close to the sea and another landscape which was belonging to the farmlands, and there was one common feature, and that was bare soil being portrayed as a road in the farmland scene and sandy soil in case of the bay scene. The information in both the cases we found that depending upon the type of enhancement technique adopted, the results have been achieved much better. By and large, one can say histogram equalization tends to over brighten the higher brightness values, whereas Gaussian stretch tends to provide a good discrimination in the central portion of the data set. In this session, I have discussed those contrast enhancement techniques wherein a single data set has been taken into consideration and its visual quality has been improved upon. In my next session, I would be discussing on those techniques wherein we will be using more than one data set to create new data sets containing informations of discrete nature. Thank you.